Okay, so this is chapter 4, lesson 4, and this is a long lesson, but there's a couple of things that we need to go over. This is going to be the last lesson in the unit. So acids are considered proton donors. And why do we consider them proton donors? Because they are able to ionize and form H+. We have monodi and triprotic acids, and what that means is that distinguishes between the number of H's. So as you can see here, we started with a triprotic acid, then a diprotic acid, and then a monoprotic. Okay, this is chapter 4, lesson 4. It's the last lesson in chapter 4. It's kind of lengthy because there's a couple of small pieces that we need to go over, and I think I'm going to change the problem set due date being because this is so long. So we'll make the problem set due date Tuesday. We're going to start with why acids are called proton donors, and that's because they can ionize and form H+ in solution. We're going to talk about monodi and triprotic acids. That's just differentiating between the number of H's that the acid has, and that affects the way that the substance dissociates. If I have a monoprotic acid, then like HCl, then the H and the Cl just dissociate. But in this instance, starting with a triprotic acid, when I first put this into water, the first H will come off and I'll be left with H2PO3. And then, as you can see down here, the H2PO3 minus 1 ion, then another H gets removed off of that, and I'm left with HPO3 2 minus, and then the last H comes off in the third dissociation. And an example of a diprotic acid, very similar, I'm going to have one H come off and I'll be left with HSO4 minus, and then the HSO4 minus dissociates into H plus SO4 2 minus. So let's talk about the strength of acids and bases. When we have a strong acid, as you've already learned, we have complete dissociation. And when we have a weak acid, we only have partial dissociation into the ions. So it's helpful to know the big 7, which are our strong acids. Notice you have all of your halogens except for fluorine. So hydrochloric, bromic, and iodic are all strong. Then nitric acid, sulfuric acid, chlorate, and perchlorate. Of your bases, your strong bases are going to be your group 1 and group 2 metal hydroxides. Summary of electrolytic properties. Remember, strong electrolytes are going to be most salts. Those are our ionic compounds, except Hg2Cl2, our big 7, and our group 1 and 2 hydroxides. Our weak electrolytes are going to be I would say most acids, except your big 7. And the only base that you really should know is weak is NH3, which is your ammonia. And then non-electrolytes is everything else. So just to review, strong electrolytes, most salts, our big 7 on the acids, and our group 1 and 2 hydroxides. The only exception to the salts is the Hg2Cl2. Our weak electrolytes are most acids, except for the big 7, and NH3 is also weak, which is a base. And then non-electrolytes is everything else. Let's review neutralization reactions. Neutralization reactions have a basic format. Well, first of all, neutralization reactions are an acid plus a base. I'm sure that you all know this, to yield a salt and water. And they have the basic format of HA plus BOH yields H2O and Ba. So where A is your cation, your anion, and B is your cation for whatever it is that you're dealing with. So let's look at a molecular equation, ionic equation, and net ionic equation for an acid-base reaction. Let's use calcium hydroxide and HCl, which is going to produce water and calcium chloride. And then we have to balance this. So 2 in front of the HCl, 2 in front of the water. Now, remember, these are all aqueous. This is the formation of liquid water, and this is aqueous. So now we break up everything into its respective cations. And these are all aqueous, aqueous, except for water is a liquid. Then I'm going to cross out my spectators. And I'm left with what forms water. So I can tell you right now that for any acid-base reaction, the net ionic equation is always going to be the formation of water, because acid-base reactions produce a salt and water, and salts are going to be aqueous. Complete and balance each of the following. So this is just getting our polyatomic ions a rundown here. So we have barium hydroxide with nitric acid, and we're going to produce water. And then I look at what's left, and barium nitrate. Barium's a group 2, so I need to drop and cross. I also need to make sure that I'm balanced. So I need 2 here for my nitrates. I have 4 H's, so I need a 2 here. Phosphoric acid, H3PO4, lithium hydroxide to produce water, and lithium phosphate. I didn't really need parentheses there, sorry. We need 3 LIs. It's going to give me 3 H's there, and 3 H's here is 6 H's there, so I need 3 here. Acetic acid, HC2H3O2, and sodium hydroxide. These are all +1, -1, so we're not going to have to balance anything on this. We're going to form sodium acetate and water. Ammonia is NH3 plus HCl. The H is going to donate here, so we're going to form NH4 plus and Cl minus. And that's balanced. Because there are other compounds that are capable of accepting a hydrogen ion, some neutralization reactions result in products other than a salt and water. Because there are other compounds that are capable of accepting a hydrogen ion, some neutralization reactions result in products other than a salt and water. And I'm going to give you a generic example first. So one is when we have a weak acid, as in acetic, and a strong base. So I'm just going to do WA for weak acid, strong base. And what's going to happen is this is going to produce Na plus C2H3O2 minus and H2O. So generically, if I were going to write this as a generic compound, it would be AH plus H2O. This could be another way to write it. Yields H3O plus A minus. So in this reaction, okay, we're just showing a weak acid with water. In another example, we might have a weak base and a strong acid. So NH3 is a weak base, strong acid like HCl. And that's going to yield, this can go both ways, these reactions, too, sorry, NH4 plus and Cl minus. If I were going to write this generic, I would have my base plus H3O plus, because that's where we're getting the hydrogens from, yielding H2O plus BH plus. So when we have a strong acid and a strong base, our pH is going to be 7. When I have a weak acid and a weak base, my resulting pH is going to really depend on the pHs of that weak acid and that weak base. Here, when I have a weak acid and a strong base, I'm going to wind up with a pH greater than 7. And here, where I have a weak base and a strong acid, I'm going to wind up with a pH less than 7. Okay, other types of reactions that take place in solutions are oxidation and reduction reactions. So here we have an example of sodium and oxygen forming sodium oxide. Remember, as you recall from Regents chemistry, anything in the free state gets assigned a 0. This is -2. This is +1. So oxidation is the loss of electrons, or as we say, LEO, loss of electrons is oxidized, and our oxidation number increases. So here I'm going from 0 on the Na to +1, so this is oxidized. Reduction is the gain of electrons. So remember, gain of electrons, is reduction, and my oxidation number is going to decrease because when I gain electrons, I become more negative. So that would be my oxygen, going from 0 to -2. And corrosion in general, which is we see a lot of oxidation reduction reactions involving metal with its environment. So just to review the oxidation rules. Oxidation number of a free element, I like to call it, is 0, meaning by itself. This also includes Brinkelhoff. Oxidation number of a monatomic ion is equal to the charge. So if I have SO4, 2-, then instead of it equaling 0, my charges have to equal -2. So oxygen is -2, that's -8. So this had to be +6 in order for the net charge to be -2. For binary compounds, the element with the greater electronegativity is assigned the negative oxidation number. And the sum of all oxidation numbers must equal the charge of the overall molecule, which is going to be 0, right? Compounds equal 0. For example, CCl4, oxygen is -1. There's 4, so that's a -4, so carbon had to be +4. So +4 and -4 equals 0. I talked about this at the beginning of the year. When you're looking at the periodic table, all group 1 metals are +1, all group 2 metals are +2. Group 13 is +3. Group 14 is plus 4 or minus 4. Carbon can go both ways. It depends on what it's combining with. And then you've got your group 15s are minus 3. Your halogens, your oxygen groups are minus 2. And your halogens are minus 1. And we always assign the top oxidation number when we're talking about nonmetals, unless it's an exception to the rule or you're told otherwise. So let's review some oxidation numbers here. Chlorine is going to be minus 1, so that gives me a net minus 3. Hydrogen is always plus 1, so therefore in this case the carbon had to be plus 2, because plus 2 plus 1 minus 3 adds up to 0. SCl2, chlorine is minus 1. That gives me a net negative 2, so sulfur had to be plus 2. And ClF3, F is minus 1. That gives me a net negative 3. So therefore Cl had to be plus 3 in this case. HNO2, oxygen is minus 2. That gives me a negative 4. H is plus 1, so N had to be plus 3, because that then adds up to 0. And here I have an ion, so remember that's going to equal the charge on the ion. So it's going to equal plus 1. My H is going to be plus 1, which is plus 4, which means that nitrogen is going to be negative 3. Okay. In addition to reacting with gases in the atmosphere, metals also react with acids or other salts in a displacement reaction, often in an aqueous solution. So this is a single replacement reaction. You're all familiar with this. A pushes B out, B gets pushed to the curb. But that's only if A is more reactive than B. So in this case, we see zinc pushes out HCl, forming ZnCl2 and H2 gas. Now, I'm just going to do the complete ionic in the middle here so you can see what's happening. We have 2H plus 2Cl minus yields. Oh, I have to balance the equation. Sorry. Oh, it is balanced. Zn2 plus 2Cl minus plus H2 gas. All right, so where are my spectators? My spectators are Cl, Cl. And that is it. So my net ionic is Zn solid plus 2H plus aqueous, yielding Zn2 plus aqueous and H2 gas. Let me do this other example down here. So we have lithium and zinc nitrate. Lithium pushes out the zinc. So again, we've got lithium solid plus Zn2 plus NO3 minus, and this is aqueous, yielding Li plus aqueous plus NO3 minus aqueous. And we need a 2 here. This one was not balanced. We need a 2 here. So this is going to be a 2. This is going to be 2Li, 2NO3 plus Zn solid. Again, looking for my spectators, NO3 minus. And that's it. So 2Li solid plus Zn2 plus aqueous yields 2Li plus aqueous, and Zn solid, which is my net ionic. How do we predict when oxidation and reduction reactions occur? The activity series. You're familiar with this. It is called Table J. And it goes from most reactive to least reactive. The metals on the top are most easily oxidized. And only metals above H can react with acids. To form H2 gas, which we just saw with the magnesium and hydrochloric acid. So here you can see that the alkali metals are more easily oxidized. If you notice, these top three are group 1, and then we do have another group 1 in here, but then these others are group 2. All right, and then you get into your transition. So that should make sense to you because we know group 1 is very reactive, then group 2, and we decrease our reactivity as we go further across the table. And here's your hydrogen. So copper, silver, mercury, platinum, and gold cannot react with an acid because they're not more reactive than the acid, so they can't push the H out, which might explain some of the phenomenon that you saw in your lab. So if we compare iron to copper, can iron oxidize copper? Here is iron, and here is copper. Yes. Can copper oxidize iron? No, because it's less reactive. Does copper react with H+? Here's copper. Here is H+. So that would be no. Does nickel react with H+? Well, here's nickel. It's above H, so yes. And is nickel oxidized by copper, or can copper oxidize nickel? And the answer is no, because copper is below nickel. Okay, which of the following metals will be oxidized by zinc? So here's zinc. So whatever zinc is oxidizing, it has to be above it. So lithium is below, zinc is below lithium, so no. Silver, zinc is above silver, so yes. Chromium, yes. Nickel, yes. Hydrogen, yes. Magnesium, no. I'm not sure what happened on the last slide. I think it cut out, so if it did, I can go over it in class. All right, to experimentally determine the concentration of an unknown solution, we perform what's called titrations. And you did this in Regents Chem. It's where you have a standard solution, so that means known concentration. And what do I mean by known concentration? I mean I know the number of moles per unit volume. And titration is using a solution of known concentration, so a standard solution, to determine the concentration of an unknown solution. Now, the equivalence point is different from the end point. So let me explain the two of these. The equivalence point is where the amount of titrant added is equal to the amount of analyte. This is where the amount of titrant added. So this is whatever you're titrating with. Is equal to the amount of analyte. And this is the substance being measured, or that you're trying to figure out. So when we say equal, okay, we're talking about H to OH ratio. Now, this is different from the end point. The end point is where the indicator changes color. And a colorimetric titration. Hypothetically, if we're very careful when we're titrating, it should be very close to where that H equals the OH. Okay, so what are we using when we do solution stoichiometry? We're going to start with grams of compound A. We use the GFM to get moles of compound A, right? And then we use the balanced equation, if we have to do a mole-mole. And then we use the molarity formula to get the volume or molarity of compound A, whatever it is that we're using. Or if we're talking about grams of compound B, it's the same process. So I just realized you were missing a slide, so I went back and I grabbed it. Titration formula. I give this as M1V1 equals M2V2. Sometimes it's M initial, V initial, M final, V final, sometimes it's MAVA equals MBVB. It depends on what you're using it for, because we can use this for titration, we can use this similar equation for dilution, so however you want to remember it is fine. Example, what volume of 0.827 molar KOH solution is required to completely neutralize 35 mils of 0.737 H2SO4? Now I'm going to show you two ways to do this problem. Okay, I am going to start with a balanced equation. So I've got KOH and H2SO4, and that yields H2O and K2SO4. And I have to balance this, and that should be balanced. All right. I'm going to start with my 35 mils of H2SO4. And I know that it has a molarity of 0.737 moles per liter. So I'm going to do 0.737 moles per liter, but this is milliliters, so I'm going to change this to 1,000 milliliters. And this is H2SO4. Then I'm going to go to my balanced equation and do my mole-mole. I have 2 KOH going to 1 H2SO4. And I know, oops, I just wrote this backwards, sorry. One H2SO4 going to 2 KOH. Now they'll cancel. Okay. And I know that I was told that the molarity of the KOH is 0.827 moles per 1 liter. So remember, this is moles of KOH, so 0.827 is going to go in the denominator, and that's per 1,000 milliliters. All right, so moles cancel, right? And when I get the math done on this, I am going to be left with 62.4 milliliters of KOH. Now, some of you might think that that's a pain in the neck, but depending on what you're given in the problem, you may need to use that. Or I can just simply do M1V1 equals M2V2, but there's a snag on this. So let's fill in what we know. We know that we have 35 mils of 0.737 molar. And we know we have 0.827 molar. And we don't know the volume. However, our H to OH ratio is not 1:1. So we have to take that into account. We need to put a 2 out here for our number of H's. And our number of OH's is simply 1. And when we do the math on this, we should get the same thing. We have 0.737 times 35 times 2 divided by 0.827, and I get 62.38, which is the same as 62.4 milliliters of KOH. Okay, let's do some examples. A 17.5 milliliter sample of acetic acid required 29.6 milliliters of 0.25 molar NaOH to neutralize it. What was the molarity of the acetic acid solution? I don't know why they write it like this. Write it the way that I taught you. That's so old school. HC2H3O2. Okay, so now let's get back to this problem. So I'm just going to use M1V1 on this one. Fairly straightforward. M1V1 equals M2V2. And one of the reasons that I'm doing this is because I'm looking at my compounds. I know that this is all 1-to-1 ratio. My balanced equation is going to produce sodium acetate and water. So I've got 17.5 mils of acetic acid, and we don't know the molarity here, but I do know that I've got 0.25 molar NaOH and 29.6 mils. So this is a simple plug and chug, and I'm going to get 0.42 molar acetic acid. Acetic acid reacts with sodium hydroxide in a neutralization reaction. If 8.3 mils of an acetic acid solution requires 42.4 mils of 0.1050 molar NaOH to reach the equivalence point, how many grams of acetic acid are in a 500 milliliter sample? Well, two things are going on here. First, I'm going to use my M1V1 equals M2V2 to find out the molarity of acetic acid. I need to know the molarity of acetic acid. I don't know that right now. Once I have the molarity of acetic acid, I can figure out how many grams are in 500 milliliters. So, M1V1 equals M2V2. I've got 0.1050 and I've got 42.4 mLs, and I don't know this, and I have 8.3 mLs. So this is going to give me 0.54 moles or molar acetic acid. Okay, so what I know is when I figure out this molarity, I know that I have 0.54 moles in 1 liter. Therefore, I want to know how many moles I have in 0.5 liters. Well, it should make sense that if 1 liter is 0.54, that a half a liter is going to be half of that, which is going to be 0.268 moles. And now I can use my dimensional analysis, and we know that 1 mole has a GFM of 60.053 grams. That is the molar mass of acetic acid, and I come out with 16.09 grams of the acetic acid. Okay, in this problem, in the laboratory, 6.67 grams of strontium nitrate was dissolved to make a 750 milliliter solution. So I know right there I'm going to be figuring out molarity. A 100 ml sample of this solution was titrated with 0.0460 molar sodium chromate. Now, we know we're going to be using a titration formula. What volume of the sodium chromate solution is required to precipitate all of the Sr2 plus as strontium chromate? And they gave us the molecular weight of strontium nitrate. So the first thing we need to do is start with a balanced equation. So this is not balanced yet. We need 2 NAs, which I now have, 2 NO3s, and everything else is good. So first thing I want to do is figure out my molarity. So molarity equals moles over liters, yes? However, I only have grams. So 6.67 divided by 211.6 is going to be equal to 0.03 moles per 750. So I'll show you that up here. So my moles equals 6.67 divided by 211.6, and that's 0.03 moles. And then I got my molarity down here as 0.042 molar. Now I can use my M1V1 and let me go with what I'm given first. 0.0460 molar. I don't know the volume on that. And we just figured out the molarity to be 0.042, and we used 100 mils. Okay, so X equals 91.367 milliliters. And that is my answer. The arsenic in a 1.22 gram sample of pesticide was chemically converted to ASO4 3-. It was then titrated with Ag+ to form Ag3 ASO4 as a precipitate. If we took 25 mils of a 0.102 molar Ag solution to reach the equivalence point, what percentage of arsenic is in the pesticide? Okay, so the first thing that we want to do here is write an equation. Okay, so here is our balanced equation. So I have 0.102 There's two ways we can do this. Let's start with 25 mils. 25 mils. And I know that that has a molarity of 0.102 moles per 1,000 milliliters. Okay? In my balanced equation, and this is my Ag+. In my balanced equation, I have 3 Ag+ going to 1 AsO4, 3 minus. So that will get me moles. Now, the other way that you could look at this is you could take your molarity and find moles. So I'm going to show the other way you can do this. 0.102 moles, right? And this is 0.025 milliliters. Wait, I'm sorry guys, I'm having a rough day. Let's use the molarity formula. Equals moles over liters. So this could be 0.102 equals X over 0.025, right? And then you're going to get 0.00255. 0.00255 moles. But what you have to realize in doing it this way is that your Ag to As ratio is 3 to 1. So you would have to divide this by 3. As what you're going to do over here, if you do that right here, you're going to get the same thing that you get here, which is 8.5 times 10 to the minus 4 moles. Because this cancels, and you're left with moles of ASO4. Now, oh, we actually needed grams. I should have taken this one more step. Alright, I'm running out of room, so I'll just come up here and do the moles to grams. I could have put it right there in dimensional. You can do it as dimensional if you want. Moles equals given mass over GFM. So I've got 8.5 times 10 to the negative 4 moles equals X over 74.9, which is the arsenic, right? And this is going to give me 0.03665 grams of arsenic. 0.0365. Okay, so they wanted to know the percentage. So that's simply part over whole, 0.0365 over 1.22 times 100. And when I do that, I get 5.2% arsenic. So there's a lot going on here because how you get to this final answer, there's a couple of ways. You can do it with dimensional analysis and get the grams of the arsenic, because honestly what I would have done right here, right after this, what I could have done, I'm going to move this up, I could have said in 1ASO4 there are 3 minus, there is 1 AS, right? And 1 AS has a GFM of 74.9. So that would, if I wanted to continue with dimensional analysis, I could have done that all the way to the end here to get my grams. All right. Or I could have done it in these smaller steps on the right where I used the molarity to figure out the moles, then realize it was a 3-to-1 ratio. I prefer dimensional analysis. I know that some of you like think in smaller chunks, and that's fine, as long as we get to the same end result and you're showing me your work. A 4.36 sample of an unknown alkali metal hydroxide is dissolved in 100 ml of water. An acid-base indicator is added, and the resulting solution is titrated with 2.5 molar HCl. The indicator changes color, signaling that the equivalence point has been reached after 17 ml of hydrochloric acid has been added. What is the molar mass of the metal hydroxide, and what is the what is the identity? Oh, there's a typo there in their PowerPoint. Identity of the metal. So they want to know basically what is the cation of the hydroxide. They want to know this. All right. So let's think about what we have to do here. Since the equivalence point is defined as where the moles of H equal the moles of OH, then the moles of the acid equal the moles of the base at that time. Right? So, if we know the moles of the acid, then we know the moles of the base at the equivalence point. And that's easy enough to figure out because I have the molarity as 2.5 molar HCl, and we know that that's 0.017 liters. So that's going to give me 0.0425 moles. And moles of acid equal moles of base because we are at the equivalence point. So if we know the moles of the base, we can then, using the 4.36 gram sample, because that's the metal hydroxide, figure out the molar mass. Because we know that moles equals given mass over GFM. And we know the moles, 0.0425, and we know the given mass, 4.36, and that's going to equal X. So our molar mass is going to be 102.59 or 102.6 grams per mole. So now we have to get a little bit intuitive. We know that all of these down here, with the exception of calcium, are going to make a monohydroxy base. So that means all of these are going to be, say, BOH. One anion, one cation. Here, this is going to be, calcium is going to be BOH2. So let's start and let's figure out what we're dealing with here. We have 102.6 grams per mole. If we subtract the hydroxide portion from the molecular weight, that will give us the mass of the cation. So we know that oxygen is approximately 16, and hydrogen is 17. So let's subtract 17 grams, right? That's going to give us 85.6 grams left. If I were to figure it out for Ca, I'd be subtracting 34 grams. But I can tell you right now, I think calcium is around 40. It is around 40. It is 40. So 40, 102.6 minus 34 is not anywhere near 40. So let's look. So we know it had to be a monohydroxy base. So let's look at the molar masses of lithium, sodium, potassium, and rubidium. And it's not exact, but rubidium is the closest. So that must have been the metal hydroxide. All right, last problem. A 1.248 sample of limestone rock is pulverized and treated with 30 mils of 1.035 molar hydrochloric acid. The excess acid then requires 11.56 of 1.01 molar NaOH. So they used a bunch of acid on this pulverized limestone sample, 1.248 grams it was. And the extra acid, excess that was not used, was able to be neutralized using 11.56 mils of this NaOH. They want you to calculate the percent by mass of the calcium carbonate in the rock, assuming that the only substance reacting with the that it is the only substance reacting with the HCl. So we kind of have to backdoor this. All right? Couple things going on. First, I want to write a reaction. So I've got calcium carbonate reacting with HCl. And that's going to produce CaCl2. CaCl2 plus CO2 and H2O. So now we need to balance this. And I have two Cl's, two Cl's, two H's, two H's, one Ca, one Ca, one C, one C, and three O's, 2 and 3. Okay, so we're balanced. The first thing I want to do is figure out, I'm going to start backwards. I need to know the volume of excess HCl that was neutralized so that I can determine how much was actually used. So I'm going to use my M1V1, M2V2. 11.56 times 1.01 and 1.035 molar. So this is going to give me 11.2 milliliters of the HCl. That was in excess. Therefore, 30 minus 11.2 is going to give me 18 no